Hi, welcome you all for this video on measurement of temperature. This is the last part of the module 5. So the series of mechanical measurements and metrology with module 5, that is the temperature measurement, is being covered in this module, in this video. Basically, temperature measurement is one of the most common and important measurement in controlling any process. It actually defines an indication of intensity of molecular kinetic energy within the system. It suggests about the degree of hotness. Commonly, commonly it is a fundamental property similar to that of mass, length, and time, and hence it is difficult to define. Temperature cannot be measured using basic standards through direct comparison. Hence, it can only be determined through some standardized calibrated devices. Change in temperature of a substance causes a variety of effects, such as change in physical state, change in chemical state, change in physical dimensions, change in electrical properties, and change in radiating ability. For most widely used temperature detectors uh, are being classified as follows. Change in physical Based on the change in physical dimensions, they are classified as liquid in glass thermometers, bimetallic elements. Changes in gas pressure or vapor pressure, they can be classified as constant volume gas thermometers and pressure thermometers. In the pressure thermometers, they can be a gas vapor or liquid filled pressure thermometers. Third one, based on the changes in chemical phases, they can be classified as fusible indicators or liquid crystals. Based on the changes in electrical properties, they can be classified as resistance thermometers, thermistors, thermocouples, or semiconductor junction sensors. Based on the changes in the emitted thermal radiation, thermal and photon sensors, or total radiation pyrometers, optical and two-color pyrometers, infrared pyrometers. Within the scope of this video, uh, or within the scope of this video syllabus, I am going to discuss on resistance thermometers and optical and infrared uh, optical pyrometers and total radiation pyrometer. Temperatures are most convenient method of temperature measurements by electrical effects are most convenient method of temperature measurement. However, for the regular usage, we use thermometers which are of liquid in glass type. The liquid in glass thermometers are most commonly used type of temperature measuring devices. The unit consists of a glass envelope, a response liquid, and a indicating scale. The envelope comprises a thick-walled glass tube with a capillary bore and a spherical or cylindrical bulb filled with liquid. The two parts are filled together and the top end of the capillary tube is sealed. The size of the capillary depends on the size of the sensing bulb, responsive liquid, and the desired temperature range of the instrument. Changes in the temperature will cause the fluid to expand and rise up the stem. Since the area of the stem is much less than the bulb, the relative small changes of fluid volume will result in significant fluid rise in the stem. The length of the movement of the free surface of the fluid column serves by prior calibration to indicate the temperature of the bulb. The laboratory work thermometers have a scale engraved directly on the glass stem, while the industry type have a separate scale located adjacent to the stem. Quite often, the top of the capillary tube is also a bulb shaped to provide safety feature in case the temperature range of the instrument is advertently exceeded. Thus, the thermometer bulb is usually filled with mercury, which all of you have seen and you have used from your high secondary school. It has the advantages of a broad temperature span between its freezing and boiling points, a nearly linear coefficient of expansion, relative ease of obtaining it in a very pure state, and its non-wetting of glass characteristics. So, mercury makes an ideal liquid which is a metal for the usage of liquid in glass thermometers. Over that, there are different other types of liquid in glass thermometers in which the toluene or pentane can be used. When measuring temperatures above the boiling point of mercury, that is 390 degrees Celsius at atmospheric pressure, mercury may evaporate and condense in the top of the stem. This is prevented further by filling the space above the mercury with nitrogen or carbon dioxide under high pressure. This raises the boiling point and allows the temperature up to 600 degrees Celsius to be measured. However, in many industrial applications, the escape of mercury through breakage causes considerable damage to the products. This may necessitate the use of other liquids such as alcohol, pentane, and toluene, which do not cause contaminations. These liquids are also used for temperature measurements below the freezing points of mercury. So these liquids have further advantages of superior readability to mercury when colored with inert dyes and of low cost. That's why generally like alcohol with dyed with red color are commonly used type of thermometer. Further, they have got low boiling points, a greater tendency to get separate in the capillary and wetting glass characteristics. The range of application of different liquids is can be like filled, syst- filled systems with the vapor, gas, or mercury of organic liquid. Many more are there. Generally, like mercury in the range of minus 35 to 510 degrees Celsius, alcohol in the range of minus 80 to 70, toluene is in the range of minus 80 to 100, and pentane in the range of minus 200 to 30, and creosote is in the range of minus 5 to 200 degrees Celsius. The choice in the type of glass used is a matter of economics, influenced by the range of thermometer. The higher the range, the higher the cost. For temperatures up to 450 degrees Celsius, normal glass is used. At temperatures above 520 degrees Celsius, borosilicate glass is being used. Above this temperature, quartz thermometers have been used, but they are not common. Some of the salient features or characteristics are like simplicity of use and relatively low cost. They are easily portable, ease of checking for physical damage, absence of need for auxiliary power, no need of additional indicating instruments, fragile construction, range limited to about 600 degrees Celsius, lack of adaptability to remote readings, time lag between the change of temperature and thermometer response due to relative high heat capacity of the bulb. Generally, thermometers are commonly used for two uh, types: in total immersion and partial immersion for calibration purposes. Total immersion thermometers are calibrated. They are being calibrated by thermometers which are commonly used of total immersion type or partial immersion type. Total immersion thermometers are calibrated to read correctly when the liquid column is completely immersed in the measured fluid. Since this may absorb the reading, a small portion of the column may be allowed to protrude with little error. Partial immersion thermometers are calibrated to read correctly when immersed in a definite amount and with the exposed portion of at a definite temperature. However, they are inherent with the less accuracy than full immersion type. If the exposed portion is at a temperature different from that at calibration, then the correction must be applied. Corrections are full and partial immersion thermometers used at conditions other than those intended are determined most accurately by the use of special Fadden thermometers. They are designed to measure the average temperature of an emergent system. If such a temperature thermometer is not available, the correction may be estimated by suspending a small auxiliary thermometer close to the stem of the thermometer to be correct. The auxiliary thermometer estimates the mean temperature of the emergent system. Now let us move to the electrical based thermometers or temperature sensing devices. These are the most convenient method of temperature measurement because they provide a signal that can be easily detected, amplified and are used for control purposes. Further, they provide accurate results when properly calibrated and compensated. Resistance thermometers. Resistance, which are generally called as resistant temperature detectors or RTDs. Resistance elements are sensitive to temperature were first made of metals like nickel, copper, platinum and silver. The temperature measuring devices using an element of this type is referred to as resistance thermometer or resistance temperature detectors. They are the sensors used to measure the temperature by correlating the resistance of our RTD element with the temperature. The change in temperature is detected by the change in the resistance of the wire. The relationship between the temperature and the resistance of conductors can be calculated from the equation as given here. R of t is equal to R naught of 1 plus alpha into delta t, or R naught of A into t minus t naught plus B into t minus t naught whole square, where A and B are the temperature coefficients of resistance depending. So the major requirements of RTDs are like the material should permit fabrication, thermal coefficient or resistivity should be high and constant, corrosion resistant and should not undergo phase change within the temperature range. They should provide reproducible and consistent results. These are some of the major requirements for the RTD. Generally, they are used in the bridge circuits, just like in the Wheatstone bridge, which is similar to the strain gauges. The advantages of RTD are like linearity over a wide range of operating range, wide operating range. Further, they possess a very wide operating ranges. They have got higher temperature operation, better stability even at a higher temperature. Limitations of RTD are like they are low sensitive. They can be affected by contact resistance, shock, and vibration. Further, they do not require no sensing points. They require no sensing points. The higher the cost than other temperature transducers. Applications of RTD. It is widely used in the furnaces for automatic temperature measurement. They are used in medical and chemical laboratories to detect very low temperatures like dry ice and liquid nitrogen. Next is about the thermocouple. Before that, generally this resistance via RT temperatures, that is RTDs, they are generally like made up of with the resistance wire which is wrapped around a mica strip and sandwiched between two additional mica strips. So the RTDs can be used directly but with permanent installation with corrosion and mechanical protection, as it is a basic requirement of RTD. Further, next is a type of temperature sensor is thermocouple, which is made by joining two dissimilar metals at one end. The joining end is referred to as the hot junction, whereas the other end of these dissimilar metals is referred to as cold end or a cold junction. The cold junction is formed by the last point of thermocouple. If there is a difference in temperature between the hot junction and cold junction, a small voltage is created. And this voltage we refer it as EMF, and it can be measured and in turn used to indicate the temperature. Generally, these thermocouples works on the of three different effects discovered by Seebeck, Peltier and Thomson. Seebeck effect says that when two dissimilar metals or different metals or unlike metals are joined together, an EMF is generated at the two junctions. That is, an EMF exists between the points A and B as in the figure, and the which primarily a function of the junction temperature, or nothing but the amount of EMF generated is different for different combinations of metals. Whereas the Peltier effect says that when two dissimilar metals are joined together to form two junctions, an EMF is generated within the circuit due to different temperatures of the two junctions of the circuit. Whereas Thomson says, as per the Thomson effect, when two unlike metals are joined together forming two junctions, the potential exists within the circuit due to temperature gradient along the entire length of the conductors within the circuit. Generally, the circuit of the working temperature of this thermocouple can be shown in the first figure here, in which the two metals are joined by causing the two junctions J1 and J2, where it comprises of two metals A and B. They are joined together to form the two junctions, which are maintained at temperatures T1 and T2. Remembering that the thermocouple cannot be formed if there are not two junctions. Since two junctions are maintained at different temperatures, the Peltier EMF is generated within the circuit, and it is the function of the temperature of the two junctions. If the temperature of both the junctions is same, equal, and opposite EMF will be generated at both the junctions, and net current flowing through the junction is zero. If the junctions are maintained at different temperatures, the EMF will not become zero, and there will be a net current flowing through the circuit. The total EMF flowing through this circuit depends on the metals used within the circuit as well as the temperature of the two junctions. The total EMF or the current flowing through the circuit can be measured easily by the suitable device. Advantages of thermocouples are like they are inexpensive, there is no resistance laid by problems, they are fastest response, simple and rugged, high temperature of operations, tip or end temperature sensing limitations are like least sensitive, non-linear, low voltage, least stable and repeatable. Coming to the laws of thermocouple, first is law of homogeneous circuit, which the first diagram says that if the two thermocouples are at junctions T1 and T2, then the thermal EMF generated is independent and affected by temperature distribution along the wires. Further, a thermocouple shown with the junction temperature at T1 and T2 along the thermocouple wires, the temperature is T3 and T4, that is along the metal A and B respectively. The thermocouple EMF is however still a function of only the temperature gradient T2 minus T1. Whereas the second law, that is law of intermediate metals, states that insertion of an intermediate metal into the thermocouple circuit will not affect the net effect EMF provided the two junctions provided by the third metal are at identical temperature. That is, when a thermocouple are used, it is usually necessary to introduce additional metals into the circuit. This happens when an instrument is used to measure the EMF, and when the junction is soldered or welded, it would seem that the introduction of other metal would modify the EMF developed by the thermocouple and destroy its calibration. However, the law of intermediate metal states that introduction of third metals into the circuit will not have any effect upon the EMF generated so long as the junctions of the third metal are at the same temperature. Hence, welding or soldering will not affect the overall temperature. Law of intermediate temperatures. It states that if a simple thermocouple circuit develops an EMF E1 when it is at junction when its junction are at T1 and T2, and EMF E2 when its junction are at temperature T2 and T3, then the same circuit will develop an EMF E3 which is equal to E1 and E2 when its junction are at T1 and T3. In other words, sum of the EMF developed by a thermocouple with its junction at temperatures T1 and T2 and with its junction at T2 and T3 will be same as the EMF developed if the thermocouple junctions are at temperature T1 and T3. And this law is useful in practice because it helps in giving the suitable correction in case of reference junction temperature other than 0 degree Celsius is employed. For example, if a thermocouple is calibrated for a reference junction temperature at 0 degree Celsius and used with a junction temperature at 20 degree Celsius, then the correction required for the observation would be the EMF produced by the thermocouple between 0 degree Celsius and 20 degree Celsius. Let us go with the thermocouple materials and construction. Generally, thermocouples are manufactured from various combination of base metals like copper and iron, base metal alloys of alumel, that is an alloy of nickel, manganese, aluminium and silicon, chromel, that is nickel and chromium, constantan, that is an alloy of copper and nickel, nitrosyl, it is an alloy of nickel, chromium and silicon, and nickel, it is an alloy of nickel, silicon, manganese, and the noble metals like platinum and tungsten, and the noble metal alloys of platinum, rhodium and tungsten or rhenium. Only combination of these are used as thermocouples, and each combination is known by internationally recognized type letter. For example, K-type thermocouple is made up of chromel alumel. The details regarding the different types of alloys, you can Google it, you can get easily. For the properties of this material should be like they should be have a linear temperature EMF relationship, and they should have high output EMF. They should be resistant to chemical change. They should possess the stability of EMF. They exhibit the stability of EMF, and the mechanical strength should be higher. Some of the different types of thermocouples you can see here. One is for resistance welding, because of which the junction is created, and the twisted wires are being used. The this is one type of thermocouple, whereas the other thermocouple insulations like elements with bed insulators are being used, or the thermocouple with noble metal wires using arc welding is done, and it is being used as a thermocouple. These are some of the different types of thermocouple structures are being used. And for the measurement of thermal EMF, the magnitude of EMF generated by the thermocouple is of 0.01 to 0.07 millivolts per degree Celsius, which is very good enough. However, the other advantages are something like they are less expensive when compared to RTD, and convenient for measuring the temperature at a particular point. Some of the limitations, as I already mentioned, like one is they have got low sensitivity and high inaccurate. Protection against contamination should be given, because they are dipped into the metals in some applications. They should be placed at a particular place so that they request no point sensing. Higher cost than other temperature transducers. These are some of the limitations. There's one more is like resistance based temperatures measures is like a thermistor. A thermistor is a type of resistor whose resistance strongly depends on the temperature. The word resistor is a combination of thermal and resistor. A thermistor is a temperature sensing element composed of sintered semiconductor material and sometimes mixture of metallic oxides such as manganese, nickel, copper, cobalt and ferrous, which exhibits a large change in resistance proportional to the small change in temperature. Pure metals have temperature coefficient of resistance. Alloys have nearly equal zero temperature coefficient of resistance. Semiconductors have negative temperature coefficient of resistance. Thermistors can be classified into two types: positive temperature coefficient thermistor, in which the resistance increases with the increase in temperature; negative temperature coefficient thermistor, in which the resistance decreases with the increase in temperature. Generally, the characteristic of the is NTC, that is negative temperature coefficient thermistor, is more common. The resistance decreases as the temperature increases. Further, they have got advantages like they are simple and easy to owing to their small sizes. Their cost is also very low. They are highly sensitive and they can be adapted to various electrical readouts with the help of computers. Thermistors can be easily used for accurate temperature measurement. Limitations like the temperature versus resistance curve for thermistors are highly non-linear. It is not rugged and requires delicate handling, which limits its application. They are susceptible to self-heating errors. Their range is limited to few hundred degrees Celsius. Thermistors use semiconductors which are prone to permanent decalibration. The application of thermistors are used in automotive applications, instrumentation and communication, consumer electronics, food handling and processing, military and aerospace. So this is about the resistance based or electrical type of temperature sensing devices. I hope I have covered to the scope of the VTU syllabus. So if you have got any doubt, please post it here or you can mail it. As a disclaimer, I hereby declare that I have used different resources, including textbooks and internet resources, for preparing this teaching material. I acknowledge all those sources through this video, and I also thank to them. And thank you all uh, for watching this video, and thank you those who have helped me to prepare this video. Thank you. I'll meet you with the another temperature measuring devices, like based on the pyrometers. Okay. uh, I hope I'm clear with this. Thank you all.